today. We have Daniel from the University of Bonn, who's going to tell us about minimizing the spatiotemporal underpinnings of the Humean mosaic. Daniel?
Yeah, thank you for having me at the conference. It's a great opportunity to speak with you all. I've noted down several connections with the talks which happened previously today, so I'm sure they'll come out as we discuss this. So I just wanted to start a timer. Helps me pace. Great. Okay, so as Enrico said, we'll be minimizing the spatiotemporal underpinnings of the Humean mosaic in this talk. So that's the goal, to do this minimization. But first I'll start with some review of what's been done before, where things stand now. So I'll look at sort of canonical Humeanism about laws in terms of Lewis. We'll take a brief look at superhumanism and the regularity relationism of, say, Huggett and Pooley and Stevens and such. And we'll look at what spatiotemporal underpinnings are assumed in these. And then, the latter two views in particular build on the sort of Lewisian view by eschewing some, but not all, aspects of space and time from the primitive ontology. And then they sort of want to recover those omitted space-time structures via a best systems analysis. But what I'd like to ask in sort of the second half of the talk is, can we go farther? Can we give a best systems analysis that accounts for every aspect of space and time, including which relations are to count as spatiotemporal? Right? So even what qualifies as spatiotemporal will be the subject of a best systems analysis. But as always, we'll kind of start with Lewis. So here's a quote that maybe we've all read from Lewis already. Humean supervenience is the doctrine that all there is to the world is a vast mosaic of local matters of particular fact. There's one little thing and then another. And then this bold portion, it's my bolding, and we'll come back to this several times, so let's remember it. We have geometry, a system of external relations, of spatiotemporal distances between points. But what are those points? Maybe they're points of spacetime itself, maybe points of point-sized bits of matter, or ether, or fields, maybe both. He's very vague about this at this point. And so from this quote, and he goes on to say all else supervenes on that, right? The standard kind of Humean story. So Lewis could be read here as a substantivalist, if you'd like to. If you take these space-time relations to be about between space-time points, then he's got a kind of substantivalist Newtonian vision going on here. But he also offers us a possibility to be a relationist along the lines of Leibniz. If we think of point-sized bits of matter, ether, field, it's matter in the relations. So Lewis, at least in this quote, could go either way. But we're interested in minimizing, so we're going to set aside that substantivalist view and look at more relationalist visions of the Humean mosaic. And in particular, I'd like to briefly talk about superhumanism. So here's Esfield and Deckert, and they have some axioms that they list. This is from their book. There are distance relations that individuate simple objects, namely matter points, and the matter points are permanent. The distance is changing between them. Everything else comes as a means to represent change in the distance relations. And again, it's a best systems analysis, so they're going to say something about simplicity and informativeness. Okay? They then follow the sort of usual Humean program. All else supervenes on that very minimal ontology that they just said. But given that sparse ontology, quite a few things have to supervene on what was just described. They'll get the laws of nature, of course, because it is a Humean view. But they'll also have to get the 3+1 dimensionality of the world. Their distance relations are just magnitudes. They're not three-dimensional separations, in some vector space. So they'll have to get the dimensionality of the world, the overall topology of it. It's like a Euclidean plane. It's connected around or twisted in some way. They'd have to somehow discover that from the network of distance relations, curvedness, flatness, standards of rotation. All of this is going to have to somehow come from their very minimal ontology. And so these other aspects of the world's topological and geometric structure are going to have to come, again, their spatiotemporal significance by winning some kind of best systems analysis, some kind of contest. Right, so everything else comes in as a means of representing this stuff in a BSA kind of way. Okay, so that's very quickly the superhuman program, and you've seen they've gotten rid of almost all of the spatiotemporal structures, but they've kept the distance relations, which they privilege in a way that Emily mentioned to us as well. But you might want to go with a different kind of primitive ontology. We don't have to go with point-like particles. Here's, let's go back to the Lewis quote, which I've restructured here as a list. So we have spatiotemporal distances between points. Those could be points of space-time. We have the substantivalism. Okay, we've seen superhumanism. But what if we want to deal with fields or particles and fields or something like that? Can we have another kind of extension of Lewis that does this? And yes, we can, which I'll spend the next few slides reviewing. So we can minimize the spatiotemporal underpinnings while kind of assuming we have particles and fields. And by the way, feel free to interrupt at any point. Just raise your hand. I'll call on you. So, okay, I'm sure we've all seen space-time diagrams. So here is how I'm going to run the next few slides. We'll talk about some space-time diagrams as a kind of stand-in for a Humean mosaic in a way. So if you haven't seen them, space-time diagrams are like stacks of movie frames, okay? You cut up movies into every frame and stack them, you get an extra dimension of time going kind of upwards. And here we have some point-like particles. They're point-like at each slice on each movie frame, but they make extended tracks up in time, right? So that's a space-time diagram. And the black and white in the background represents a field, something like electromagnetism, waving around in space. And you see kind of the particles move in some kind of relation with the field in the background. Okay, here's a more complicated, larger space-time diagram, and this is actually the one that we're thinking about. There's different particles have different charges, let's say, and they respond to the field differently. Okay, it's just a generic example. But note, and this will be important later, the green particle here is neutral, moves on a straight line, doesn't respond to the field. Okay, so one of them seems to be neutral, the other one seems to be charged in some way, and we can maybe do some analysis to figure that out. Okay, and then we'll think of this like as a Humean mosaic. Okay, we're given some kind of, there is some distribution of fields and particles moving around and such, and we want laws for this. So looking at that space-time diagram, one might, in the usual kind of Humean way, look at it and try and systematize the behavior of the field and the particles. Here are three laws that you might arrive at looking at that picture. And these are actually the laws that describe that behavior. It's actually correct. But don't worry about the details, but the first equation there is the Klein-Gordon equation. We don't need to know anything about these equations in particular. I just want to be concrete as I talk about things. So it's a Klein-Gordon equation for a massless scalar field with some charge density. The second equation says that the particles always move slower than the speed of light. And I've written all this all down in some coordinate system. We'll get rid of the coordinates in a moment. And then we've got the special relativistic version of Newton's law. They're responding to some forces due to the field or such. Right? It's all very standard physics. But here's the important part. We can rewrite these equations and get rid of any reference to the coordinate system. I had some yellow lines here. We don't need those. Okay, let's get rid of them. Coordinate artifacts, we don't like them. Okay, so as I'm sure most of you are maybe familiar, you can rewrite your physics in a coordinate-free language of differential geometry. These are the same three equations as before. I've just rewritten them so they don't reference coordinates anymore. We had to introduce some new mathematical structures. And these will be our next targets of metaphysical questioning in a moment. So we've got the field now. It's a map from a manifold M, just a smooth manifold, just a topological space with some smooth structure. Okay, it's mapped from there to the real numbers. And the particle trajectories are just the reverse. They take real numbers and map them onto the manifold to give us a trajectory. Yeah, the manifold's just a topological object, but then there are some geometric structures hanging around. We've got a Lorentzian manifold, a connection, all this kind of stuff. Right? And equation 6 still says that force-free particles travel in straight lines, but straightness is not checked against the t, x, y, z coordinate system like it was before. Straightness is here, is defined in terms of some geometric structures defined on the space-time. Okay, why am I going through all of this? Because now we have this kind of metaphysical picture of the world. If you take a naive kind of realistic stance of those equations I just wrote, you have your particles and fields moving around. They are defined on some kind of topological space, which is this black and white space. But then there's also, merged in with the structure, but I've separated it so we can see it, a kind of Lorentzian metric in the background. So we've got our space-time topology, the kind of events, a stage where the world's events happen on. It's continuous, connected, has some dimensionality, but no like notions of distance or straightness. That's all handled by the space-time geometry. Okay, so we've got this kind of picture of the world where we're at the moment taking the space-time structure really in a very strong realist way. But now think, again, this is a Humean mosaic, so that's the geometric structure of the Humean mosaic then, right? But does this Humean mosaic really need any of these geometric underpinnings that we've seen to underpin it with? So Harvey Brown asks, and I really like this question, how do the force-free particles know which way straight is? You've got the particles moving here on this topological sheet. Do they have to somehow consult with the geometric substructure of the world to know which way straight again? Oh, it's that way, and then they're sort of guided or consulted by the geometry. That seems a little bit strange, especially if we have intuitions against governing laws. It still seems like there's some sort of structure out there which is, the particles can't get by on their own. They need to consult with something or be told what to do or something like this. So if you have those kinds of intuitions, this might seem strange. The particles might just move under their own dynamics somehow, irrespective of the background structure, or they might just be there, spread out in the way they are, if we want to accept that as a brute fact. But potentially we can apply a best systems analysis to the geometry that's there in the background. And it'll come in later as we systematize the dynamics, not doing a fundamental role in facilitating the dynamics. Okay, so that's when we get to this view of regularity relationism, developed by Huggett and Cooley and Stevens. If we want to do a kind of best systems analysis for the geometry in the background, we're going to need options. We need different possibilities to think should be in contest with each other, and some arises as best, right? And as this demo shows, and this demo, all these figures are in the kind of theory, something I've made up that I think very well demonstrates what's going on here. There might be multiple sensible ways, maybe one's best, but multiple are sensible anyway, of associating the particles and fields with this fixed background. So here, remember, the green line is straight, but there's a way, and it's actually a conformal transformation, if you care about the details. I can stretch and squish that topological sheet without changing its topological properties, but it's now associated in a different way with the geometric background. But notice what I did, the orange lines are straight now. I continue to do more conformal transformations, and now the red lines are straight. Okay, so there's different ways I can stretch and squish this topological sheet, this extended distribution of particles and fields. There the orange lines are straight again, green lines are straight, now the blue lines are straight, and now the purple line is straight. Okay, so I have a free play in how I associate the distribution of matter with the geometric background structure. Now we have options, now we can compare the options, now we can do a best systems analysis, and by some means select one of them as best. Okay? And in this one, it seems like it's actually a pretty fair choice between all of them. There may be some subtle things that help us pick out one or the other, but there are options. We have choices. We can mark one as best. Okay? And if we adopt this kind of best systems account of geometry, which I've demonstrated just here, geometry might still be real, and if you care about this kind of thing, it might be objective and mind-independent, analogously to how Humeans think that the laws of nature might be nonetheless be real, even though they're non-governing. Okay, so in particular, regarding the geometry, there might be an objective, non-conventional fact about which geometry is best, and I'll call that Lorentzian metric eta best. So it might be an objective choice of which is best. Maybe there isn't, that's something you have to argue for, but it's possible that there could be a best geometry. And then what makes this mind independent, our usual claims about distances and durations, intervals and such, might then truly report the values of certain integrals with respect to this best metric. You do integrals and do your thing about the subjectively selected metric, and there are facts that everyone should agree on about based in the mind-independent world. So you can have objective and mind-independent geometry, but this is how I understand the dynamics first view of geometry in the style of Brown and such, and paralleling the Humeanism about laws, is that the claim here is that there's no hard-working geometric structure out there really built into the mosaic which is directing and guiding particles around, just like there's no governing laws, according to the Humean, right? So per Brown, this metric that ends up arising in our theory, it's there, it's real, objective, mind-independent, but it's not doing any geometric work. All of its proto-geometric significance comes only by virtue of how it features in the dynamical equations of the rods in flux. This is how I understand Brown, and I hope the analogy with Humeanism is fairly clear, because now I'd like to extend this as we move on to our further considerations about getting a more significant best systems analysis for space and time. Okay, so just any questions at this point? So that's the review of kind of how people have chipped away at the spatiotemporal underpinnings of the Humean mosaic in the past, and I'd like to go farther now. Are there any questions about that, or was that all old hat for everybody? Yeah?
Just to clarify, is the statement that the metric appearing in the dynamical equations for particles does not have per se a spatiotemporal characterization, or is the statement the stronger one that there's no metric?
Let's see. So the metric, okay, the metric does appear here in the force law. Yeah, so the metric and the connection are in the force law. But I think the idea of the view I was staying here is if you want a Humean mosaic without any geometry, right, then you just focus on the Humean mosaic as this topological sheet that I was bending and stretching around. It's just a fact about the way the particles and fields are distributed on it, right? And it just so happens there's a nice geometric way of associating a geometric structure with this, which then facilitates us writing down the dynamics. I can't write down these dynamical equations without the metric, right? So introducing them. Sorry, these equations, the way they're written in the language of differential geometry, they involve the connection and the metric. Yeah. If you didn't let me write this symbol, I couldn't write this equation.
Yeah,
right?
Exactly. So the metric and the connection are there.
They're there in the dynamical equations, but the dynamical equations aren't doing any law-like governance. What I'm saying is the world is just this topological sheet of a distribution of fields and particles as they move around. Now, I want to describe that in terms of laws as a good Humean, right? I start to try and think of how to write down the laws. Well, I can't write them down, it turns out, I can't write down any good laws anyway, without introducing this geometric structure. So it comes in at the same time as the laws, in the same manner as the laws, as a way of systematizing what brute reality is, which is just this topological sheet of sort of distributions of matter and fields.
But that's true also for the mass, the charge, and so on. You read them out of those.
Yeah. Okay. For the charge in particular, you could go either way. I think you could either put the property of charge onto the particles, or see it as coming out as a parameter of the laws.
Yeah.
Somehow. You could go either way. I think. Yeah. Okay, well, this is how I understand the dynamics first view of geometry, but there's other ways of thinking about it, potentially. Okay, any other questions at this point? Here? Okay. No? Okay, we'll continue on then. Okay, to summarize those two approaches that we've seen, the superhumanism and its regularity relationism I talked about. The world's populated by some primitive matter content. Could be fields, could be particles. It's kind of to taste what you like your primitive matter content to be. Okay, and those stand in some kind of primitive spatiotemporal relations. For superhumanism, that was distance relations. For the primitive ontology, though, for the regularity relationism, there was no geometry. There were no distances before we added them in our best systems analysis. There was just this kind of primitive topology spread outness of the stuff in a non-geometric way. And everything else should come, or supervene on top of that kind of meager ontology by winning some kind of best systems analysis. Now, John Norton has a complaint against this dynamics first view of geometry he raises in this 2008 paper. It's basically that it doesn't go far enough. Tacitly, this view already assumes an existing space-time endowed with topological properties. There's kind of a space-time on which the particles and fields live. There's still stuff there, there's still space-time points there. And so it antecedently presumes the essential commitments of a realist conception of space-time, says Norton. And he goes on to say, the problem with this kind of view is that it becomes less interesting the more spatiotemporal properties it assumes, and I agree. And so I'd like to get rid of them just to kind of see how far we can take this program. I mean, Emily had other reasons for trying to get rid of them, but I just want to see them go because Because we could do better. We could incorporate more into our best systems analysis. Okay, and a similar complaint can be raised against the superhumanisms. It doesn't give a BSA account of every aspect of space and time. Some set of relations are picked out as very privileged, these distance relations, and then they are they're in the fundamental ontology in a privileged kind of way. Maybe we can get rid of that. And so this is the kind of project I've been engaged in my DPhil thesis. I show there how we can apply this best systems analysis to every aspect of space and time. And the way this goes farther is it includes which kinds of relations are to count as spatiotemporal. And you might think, well, any kind of world comes with a fact about what's spatiotemporal, but it doesn't, actually. And we'll see this when we look at space-time dualities. So if we want such an all-encompassing best systems analysis covering really every aspect of space and time, just like with geometry, we're going to need some options to compare. We need an ability to move between different options, compare them, assess their virtues, have selection criteria, get a best systems analysis going. So we're going to need a host of contests between various, sometimes radically different space-time framings of our theories. Because if this framing of the theory and that framing of the theory disagree about which relations are to count as spatiotemporal, they're going to look quite different. Okay? And these are what we find in space-time dualities. So my DPhil thesis develops some powerful new mathematical techniques. I call it the ISE method, but I really won't be able to get into any of the technical details of how it works. But I built some new techniques to let us host this contest, move between these space-time dualities so that we can start to investigate them and maybe launch a best systems analysis based on them. So what are space-time dualities? I'll show some examples and we'll talk through a few. There are instances where we've got two or more theories. It says duality, but it could be more than two theories. Don't worry about that. There's a kind of structural equivalence between the theories in the way I will specify a bit later on. And they're structurally equivalent in a way, but when you look at them, they present themselves as about two radically different spatiotemporal descriptions of that structure. Okay? And a cutting edge example would be the ADS-CFT correspondence, something like this. So certain field theories take place in the bulk, in our usual 3+1 dimensional spacetime. Well, not ours, but ADS, There's an equivalent description of these kinds of theories in terms of a different type of field, conformal fields, living on the boundary, which is a 2+1 dimensional spacetime, right? And so they're disagreeing fundamentally about the structure of space and time, these two presentations of the theory. And some believe that the boundary description is more fundamental in a way, for some quantum gravity arguments to do with black holes and information and other reasons. But it could be that's fundamental and that the bulk arises as a kind of hologram. Okay? I won't talk any more about the ADS-CFT stuff because it's too complicated. Okay? If we want philosophers to do work on this, we really have to find a simplified example of space-time dualities. And I've got several in my thesis that I discuss. But here's the kind of simpler working example, which I think it's easier to wrap our heads around. And it's developed new in my thesis. It's the Mobius-Euclid duality. So what does that look like? Certain theories about point-like particles floating around on the Mobius strip. So here's space, it's shaped like a Mobius strip. It's a weird world, there's just one particle, but it floats around the Mobius strip and does what it does. I'll give more specific dynamics later. But there's a way to topologically redescribe theories of this kind as being about a different type of particle, an extended line-shaped particle that would have a world sheet in space-time. But anyway, that kind of particle floating around on the Euclidean plane. It turns out there's like a really nice one-to-one correspondence between these two. So let me describe the theories in a little bit more detail, because this will be kind of an example I'm going to keep coming back to through the talk. Okay, so here's that particle about the point on the Mobius strip. A bit of terminology. The Mobius strip is a fiber bundle. I'm going to say the word fiber sometimes. But by that I just mean like this black line, these sort of sections of the Mobius strip that vertically cross this dashed blue line. Right, so it's divided up into a bunch of fibers as it goes around and they twist around and reconnect. Okay? But if the particle is to stay on just one fiber, then it oscillates harmonically back and forward. I'm just making up some dynamics, okay? And if it's crossing the fibers, it will continue to do so at a constant rate. I'm just stipulating some dynamics for the theory. Okay? Here is what you might consider to be a completely different theory. Now space is the Euclidean plane, not the Mobius strip. And the particles not point-like, it's line-shaped. And again, so it'll have a world sheet in space-time. It's rigid and straight and perfect. Okay? But what it can do, there's a special blue point, and the line can oscillate harmonically back and forward across the point. Or if the line happens to be rotating, it keeps rotating at a fixed rate. Those are the two things the line does. Okay? It's just a strange theory I've made up. But these two theories that I described in a kind of deep structural way, they're equivalent to each other. Okay? And I'll hopefully demonstrate that a bit quickly so we can use this as our working example through the later portions of the talk. I'm happy to take questions about this because it's a little tricky how exactly it works. But it turns out there's an isomorphism between the space of all lines in the Euclidean plane and the space of all points on the Mobius strip. I'm going to highlight that isomorphism. But I designed these two theories. Mathematicians know about that isomorphism. I didn't come up with it. But I built space-time theories on top of it to make it a duality. Okay, so in the Euclidean plane, there are families of co-parallel lines. If this line stayed parallel to itself and moved, it would sweep out all the parallel lines in its family. All of those correspond to points on the same fiber of the Mobius strip. So every fiber is a set of parallel lines of the plane. Distances between two parallel lines corresponds to distances on one fiber. I drew the fibers here as finite so we could see them, but imagine the fiber goes off infinitely in all directions, okay? That's just a simplification of the drawing. Now, intersecting lines are in different parallel families, right? And thereby on different fibers. And the intersection angle of the two lines corresponds to the distance between the two fibers. Where does the twist come in? I can tell you that in a moment if you like, but that's kind of the isomorphism between these two spaces. So anything this particle does, you could put in more particles. You could make them dance around in whatever way you like. Whatever kind of dynamics you place here, there's an equivalent description over there. And so these two descriptions of this dynamics, they're equivalent to each other in a very significant structural sense. All of Euclidean geometry, for instance, can be done on the Mobius strip. Right? You construct triangles, you construct circles, you construct pentagons, whatever you like. There's an equivalent construction here. Every logical statement that holds there has a different interpretation in which it holds here. These are really both models of Euclidean geometry in every sense you'd like. But they've pretty radically changed the theory's background structure, the Mobius strip versus the Euclidean plane. They've pretty radically changed what type of particles the theory is about. One thinks it's about point-like particles, the other theory says the world's about line-shaped particles. And that is related to this last point. In this case, it's a mereologically simple particle existing in the world. And there, the fundamental particles have mereological parts. Right? So it's really radically different descriptions of the world which are being related here. And this is kind of like all space-time dualities. Any questions about how this works? It's a very kind of tricky isomorphism, but I hope you can see roughly how it works and that it preserves all the structures of Euclidean geometry. Okay? Yep? Okay, great.
Sorry, just
yep.
in the map, you're not really mapping to the real line, you're mapping to the circle, right?
Sorry, what's mapping to the circle?
So, in the harmonic oscillator dual,
yeah,
the position
yeah,
of the particle that you have the harmonic oscillator is compactified. Isn't that right? Maybe I'm misunderstanding. Instead of describing the system as a particle moving on the Mobius strip,
yeah,
we describe it as an harmonic oscillator with
yeah.
The position of the harmonic oscillator
Yeah.
is you have two degrees of freedom. One is the oscillation,
Yeah.
and the other is the position along the real line.
Right.
But it's not the full real line, exactly the circle. I'm just wondering where the
Yeah.
compactness of the Mobius strip ends up on the dual description.
Yeah, well, the Mobius strip, okay, I've drawn it here as if the fibers have a finite width, but that's just a simplification for the drawing. The fibers actually go off to infinity in both directions. I just can't draw infinite copies of R twisting around.
Okay, but I'm wondering about the other one.
Oh yeah, that's the rotational direction. As this, and here I'll explain where the twist comes from as well. There's this special blue point called at the origin. Every line has a point which is nearest to the origin.
Mm-hmm.
That in polar coordinates would have r and theta as its variables. R goes along the fiber, theta goes around the loop. Okay, so it's just identifying this point in polar coordinates. So as the line moves around and sweeps around here, let's say the line moves halfway around, gets back to, so just rotates by pi. It comes back actually to the same parallel family that it started in. It's just on the other side of the blue point. What does that look like here? If this particle were to go around, it would actually come back to the same fiber it started on, just on the other side of the dashed blue line. You'd have to go around twice to get home. Do you see? Except in the case where the line goes through the blue point, or if this point was on the blue line, then if you go around once, you actually get home, because the line is unoriented. So it comes back to itself after just a pi rotation. So hopefully that clarifies what's going on.
So it means that the compactness of the supporting manifold is an invariant property in both descriptions under the duality map.
The supporting manifold, do you mean the base space of the fiber bundle?
Yeah.
Or something?
The fact that it's a compact manifold.
I'm not sure it's a compact manifold if the fibers are the real line. There's a kind of periodic direction. There's a direction which is closed around it. I mean, yeah, but hopefully my little discussion of how rotation works shows you where things fit. There's no topological invariance under these three descriptions. It's just
to the same point after moving around the Mobius strip twice.
Yeah. So going once around the Mobius strip, wherein you end up on the other side of the fiber.
And then you keep
That's not a 360-degree rotation. It's an 180-degree rotation here.
Sure.
You have to do that twice.
And then you keep
Yeah.
going and you go back to the same point. That's
Yeah.
compactness.
And if you rotate this line twice in 180 by pi, it comes back to the same line.
Yeah.
Yeah.
Two compact trajectories.
Oh yeah. Sorry. So a compact trajectory here. A closed line trajectory, which is compact here, has a corresponding trajectory here. Yeah, right. But the space that the objects live on is not compact over here. It's not really compact over here either, but it has a compact, direction to it. So it's kind of a subtle kind of duality here. But hopefully it's relatively clear how it works. And that's a neat example, right? Okay, so as this, the ADS CFT example I just mentioned, and this Mobius Euclid one we worked through a little bit, show when we make these kinds of radical redescriptions of our space-time theories, because, and let me stress this point, this theory and this theory regard different transformations of spatiotemporal, okay? There's the diffeomorphism group for the Mobius strip, right? And if you acted some diffeomorphism like that here, there'd be no corresponding action over there. It would be some kind of transformation of the state, but not a diffeomorphism. Okay, so they have completely different structures in terms of what they regard as diffeomorphisms. Right, so when we make this change of our space-time theory, it comes along with the change of the theory's matter content. Whereas one theory is about this type of particle or field on this space-time, the other theory is about that type of particle field on that space-time. Okay, when you re-describe the space-time structure so radically, you often, or almost always, have to radically re-describe the way that the particles fit, or fields fit on the space-time. And so both aspects of our previous reduction basis, the primitive type of matter, what's primitively regarded as space-time relations, these are in play and can now be subjected to a best systems analysis, if we like. and in a way this is a generalization of Leibniz's package deal, thought that the various parts of our theories come together as a package deal, including their laws, their ontologies, their properties, and now their spatiotemporal underpinnings. How you choose what is spatiotemporal reflects or constrains how the objects of your theory appear on that space-time. Okay, but how would such a view work if you really want a best systems analysis that sort of goes or covers these space-time dualities? For inspiration, I'm going to look to Hall, Ned Hall, his unofficial guiding idea behind Humeanism about laws. Here's a quick quote. By taking standards, here's what Humeans do. They take standards that both sides of the debate endorse. These are epistemic standards for picking up the laws, right? That the anti-Humean opponents regard solely as epistemic standards. Right? So we all agree that this process of informativeness and simplification, sure, epistemically that's how we find the laws, that's how we go about our epistemic journey to discovering the laws. But then the Humean wants to say that that's it. We've elevated then those epistemic standards to be constitutive of the laws of nature. In Ned's thinking, this is what the Humean move is. So to paraphrase, the laws of nature on a Humean account don't earn their nomological significance by having some hard-working, law-like governing counterpart out there in the world. The nomological significance comes from a kind of best systems analysis. It comes from them being, in some sense, a particularly nice way of systematizing the world's dynamics. So that's how it earns its nomological significance. So I want to extend that kind of view, along with the kind of dynamics first view of geometry we saw before, to now accompany all parts of the space-time manifold. So what I want to say is the space-time manifold that appears in our theories. I showed you an M, that topological, or that smooth manifold. I want to say it doesn't gain its spatiotemporal significance by latching onto some actual stage which is supporting the players as they move and carry out their drama. So rejecting Newton here. I also want to say the space-time manifold doesn't get its significance by latching onto some fundamental space-time relations that are key in facilitating the interactions between the players in the drama. Right? So it's not a relationalism either, it's contra Leibniz in that way. So instead, the space-time manifold is going to acquire its spatiotemporal significance, not just parts of it, wholesale, by being a particularly nice way of systematizing the world's dynamics. So it's coming into the world not as corresponding to a substance or any kind of relation. It is an organizational principle that we're bringing to the world as a kind of way of best systematizing it. But it doesn't have to be, maybe it's an objective fact in that room. Yes? Mm-hmm.
Sorry, what are we systematizing?
Yeah, great question. We'll come to this.
Okay.
We'll come to this. Well, it's here grammatically in the sentence. We're systematizing the world's dynamical behavior. But what does that mean exactly? Yeah.
Do you already need space-time?
Well, that's debatable. It's unclear if you need time for dynamics or dynamics. Like, does time precede dynamics and change, or does change precede dynamics? It's unclear. So, if you want to think about dynamics in time, time would have to be somehow emergent, and there's some other conception of dynamics going on here. Right. But by the world's dynamical behavior, I mean, okay, I'm about to make a connection with Kant here. So this extension of Lewis's best systems analysis to space-time in this very all-inclusive way that I'm doing, in some ways, and I've thought about this a bit and we can talk about it more, it's parallel to Kant's extension of Hume's work on causation to space and time. Right? So Lewis has the development of Hume, right? Kant extends Hume to space and time. I'm extending Lewis to space and time. Oh, there's a square. So it's like I'm moving parallel. Okay. So what's this dynamical behavior? It's something like the noumenal world. Okay. I'll buy into a kind of structural realism later, and it's that whatever there is that we can only characterize structurally. But that's a later claim. Okay. And actually, yeah, this is the next slide. So don't we need a concrete statement of what the reduction basis is? Like, what's the supervenience basis? This previous slide, I phrased it in a particular way. It only makes a claim about the space-time manifold that appears in our theories, gets its spatiotemporal significance via a certain kind of route. via kind of epistemic pragmatist route. That's where it earns its merits as spatiotemporal. Just defending that claim doesn't require me to posit a reduction basis. Okay? Just like Kant doesn't have to say much about what's going on in the noumenal world. Right? I'm saying the process via which the concept gets into our thought and earns its metaphysical credentials is of a certain kind rather than a certain other kind. That's the claim I'm committed to here. But I will make an ontological proposal at the end of the talk, if people insist upon that. But anyway, in line with Hall's unofficial guiding idea behind Humeanism about laws, we're supposed to take epistemic standards and then elevate them to a metaphysical account. So let's not get to the metaphysics too quickly. Let's really now think about the epistemology of space and time, particularly space-time topology. And let's see what we find, and then maybe we can build a metaphysics on that later. So we'll get back to the reduction or the supervening spaces later, if we like. Okay, but this possibility of space-time dualities raises some significant questions about epistemology of space and time. So how do we come to pick out topological properties of space and time? Connectedness, continuity, dimensionality, these kinds of things. How do we associate those with the world? When multiple stagings are available, as they sometimes are in these space-time duality cases, what's our topology selection criteria? How do we go about competing these alternate views of the world which we might mathematically construct? So some considerations that come to mind are like low dimensionality is in some ways preferable. And these are all related to simplicity. We want symmetries to be represented in a nice way. We want local dynamics. If I provide you some terribly complex description of the world with non-local dynamics and high dimensions, and it just seems like an inelegant way to go. And so we can evaluate then these kinds of selection criteria, and I do some case studies in my thesis. But then some more interesting questions are, where do these topology selection criteria come from? Are they going to be objective in a way, forced on us by reason itself, or is there some element of conventionality to them? A middle ground, perhaps they're objective, but only relative to human phenomenology, or our particular epistemic goals or cognitive limitations. So it's a kind of, in the laws context, Walter Ock calls this Humeanism with a face. So Humeanism with a human face, right? So it's the best laws for us, but motions might have different laws. And so for instance, in a kind of Mobius-Euclid world, or ADS-CFT, or any other kind of space-time duality you might think of, could it be that one rational civilization moves around and thinks of itself and works in terms of the Euclidean representation here, whereas some other rational civilization opts for the other kind of view, and then they bump into each other somehow in space and are very confused about how to even talk to each other or how they're ascribing different ontologies to the world. And is one right then? Or could it be that there's two rational ways of going, maybe depending on your personal physiology, right? Okay, so here's a little case study, and then we'll wrap up with some conclusions. Here's a theory. It's set on a space-time manifold. There's two extended dimensions here, one of space and one of time, basically, and then two compactified dimensions of a sphere. So it's a 1 plus 1 dimensional world with some compactified dimensions. There's a field on it. It's just a scalar field. That's what the theory is. That's what the world is. And it obeys this Klein-Gordon equation. Okay, it's the Klein-Gordon equation, and then some derivatives in the generators of the rotations about the sphere. So this is just the Klein-Gordon equation on that space-time with the standard metric it would have. Okay, but looking at this theory, you can do a harmonic expansion of this field, which again is spread over these compactified dimensions. And here is the spherical harmonics. L and M are the quantum numbers that we all know and love, right? But let's focus in on these coefficient fields that we have here. They just depend on T and Q. The angular dependence is dropped out of them. You can look at those fields, and you can pretend they're fields on a two-dimensional space-time, if you want to, right? So now we're just on M nu being just R squared, right? So we've lost our compactified dimensions. They've fallen away. And you can find out what dynamical equations these satisfy. And turns out they satisfy a Klein-Gordon equation, just with an increased mass. So there's like a confinement mass that's being added on here. Okay? So it's an infinite number of increasingly massive Klein-Gordon fields, but on a lower dimensional space-time. Okay, this is a case where we have two space-time framings of this theory. One is about a single massive scalar field on a space-time with some compactified dimensions. The other view of the theory, no, space-time is really it's lower dimensional, just two-dimensional, but it's about an infinite collection of massive scalar fields without any compactified dimensions. These are two ways of parsing this theory in different kind of spatiotemporal terms. Is that clear? I mean, this is just a very simple example of I say at the top, a Kaluza-Klein-like dimensional reductions. It's the simplest one you can imagine. Now, how would we come to decide which of those two views of the world is right? We want to find out the epistemology of this, our kind of topology selection criteria. What are they? How do we come about this? Imagine that we've got some 1 + 1 dimensional physicists, or they like to think of themselves as such, and they live in a world where this compactified dimension is very, very small. Or analogously, all the masses except L = M = 0 are very, very large. Because the masses here, the extra bit of mass goes with 1/r². Okay? So either way, on either view of the theory, in the r goes to 0 limit, they're going to think they have a single massive field in their world, and that it's 1 + 1 dimensional space-time. Because all the other LM fields are just too massive. They're frozen out. They just don't appear in the physics. Okay? So the physicists then, they probe higher and higher energies. As you do, you build a large hadron collider and such, and you discover, oh, there's more massive fields. We found a new hierarchy and they find this trio of fields with L = 1, and M being what it can be. And then they find a quintuple of fields, a little bit more massive, and then they find more and more. And they figure out the pattern, and they figure out, let's say they figure out this formula, okay, and they project it into the future. They think they'll keep finding these fields, and they keep doing. Okay, but what's the best way to account for all these findings? They thought they were 1 + 1 dimensional, they found some massive fields, and more, and what to account for. Some, you might call them radical, you might not. I think it's physicists suggest that this can all be elegantly accounted for by introducing some new exotic, I don't know, compactified dimensions. They're unlike anything we've seen before, little wrapped up dimensions hidden from our macroscopic view. The alleged benefits of this strange view, it unifies the symmetries. So there was an SO3 symmetry relating these LM fields. They have a kind of internal SO3 symmetry you can work out. But we can externalize that into a space-time symmetry. It would be more space-time. And then the reds are complaints against that reason. Okay? But why is an external symmetry better than an internal symmetry? The symmetries are the same in either theory. We've just chosen to make one external versus internal. It's unclear. In a way, external symmetries are worse because they come with ontological commitments. I have to buy into more space-time than I did before. Okay, so all else equal, more ontology, worse. Okay? The proponent of this view might talk about token parsimony. We had an infinite family of massive scalar fields, and now it's just one massive scalar field. Counterpoint, isn't type parsimony more relevant? Often it is, and there's arguments for that favor. Either way, there's one type of thing, massive scalar fields, and there could be several of them, several kinds of them, but not several kinds, but several instances, token instances of that type. So you really haven't improved on parsimony much if we count by type instead of by token. Okay? Both framings of the theory are completely local. If you look at the dynamical equations, it's just a Klein-Gordon equation in either case. Okay? So there's no difference in locality between these space-time framings. And the physicists have a macroscopic 1 + 1 dimensional phenomenology that they would see if they look around. Right? And both are in line with that. Both have good accounts for that. And hopefully it's clear both of these can explain every experiment. These are empirically equivalent theories. Okay? Any description of an experiment you give in one, there's a corresponding description in the other. Okay, any questions about this? Do people have a strong preference for one of these space-time framings over the other? Or is it maybe perhaps a matter of convention? Or do you think reason will come in and push us one way or the other if we think hard enough?
It is a matter of convention, but it depends what type of experiments the physicist can do. If you can individually excite the individual scalar fields, massive scalar fields, and can do a lot of physics with the individual.
What one viewport identifies as a single LM field that they can excite individually and do this. The other would call just a mode. You're exciting just a mode of this field.
Yeah, so the
So-
question is whether in the type of experiments or in physics that one is most interested in describing, a single massive scalar field is the relevant degree of freedom, or you always end up working with several of them, in which case the re-expression as a single scalar field in a higher dimension is much more convenient.
Yeah, so if calculations are more convenient to do in one frame or the other.
So
Right.
mathematically, clearly, they are equivalent descriptions.
Right. But metaphysically,
Conceptually-
ontologically, do you have a preference for one or the other? Or is it just a matter of mathematical pragmatic convenience? Or
Are you asking me or are you asking
yeah,
the
you.
physicist?
I asked if
From
people
my
had
point of
opinions
view-
about one way or the other.
From my point of view, everything is a matter of pragmatic
Yeah.
convenience. I mean, the validity of your metaphysical commitment has to be evaluated in face of the pragmatic convenience. I don't see any other criteria.
When you say evaluated, do you mean to determine if it's correct or incorrect? Absolutely, or like if it's just useful?
Correctness or incorrectness, I would be a hard time defining them independently of the pragmatic convenience.
Right.
The guy defended the epistemological law this morning.
Yeah.
But I just want to add,
Sure.
your case seems interesting because we have both. But just imagine, in most cases, probably we have the map to produce just one, and the extraterrestrial have the map to produce another one, and we cannot even compare because we don't have access to both. We take the one we have.
Oh, sure, yeah, if we're just not mathematically sophisticated enough to
The
know
case-
about the spherical
Yeah,
harmonics.
the
or
case
something.
I have in mind is the quantification of an abelian gauge theory.
Mhm.
We don't know what to do that in a reduced space, so we do it with the ghost and all kind of garbage.
Right.
But maybe the extraterrestrial, they have access to the map to do it directly,
Mhm.
and we would meet, and we would say, do we speak about the same thing?
Mhm. Yeah. Right.
So at least in your process, you presume that we have access to the different version, and we can
Yeah.
choose.
Well, it was some radical physicists, and I imagine they
Yeah.
disappeared into the woods for 10 years and came back with their funny ideas. I mean, yeah. So I mean, this is, if you haven't noticed, it's an allegory for string theory. Of course, the kinds of compactified dimensions are in a way similar. So yeah, it's some kind of radical suggestion that there's compactified dimensions, but I'm not sure. Yeah.
I'm interested whether you think that the situation changes or the answer to the questions changes if the internal space was non-compact. Because you can play the same game with R4 reduced to R2
Yeah.
with an internal space being R2.
Right.
And then you have continuous Fourier transform instead of the expansion in spherical
Yeah.
harmonics.
Yeah.
You have momentum instead of masses or the
Yeah.
momentum level. But the duality is the
So-
same.
So if the SO3 group wasn't compact, if it was R, you
Yeah.
basically,
Would you say
I would take this direction and do a Fourier transform just in that way.
Yeah.
You know?
Yeah.
The difference is that Fourier variable would be continuous and would sort of like incorporate in with the rest of the space-time. Whereas the kind of Fourier variables here are these L and M, which are discrete. I took on an interpretation of different discrete fields in a lower dimensional space-time. If it was a continuum, and I did a Fourier transform in this way,
Yeah.
I would still end up with a space-time of the same dimension, just local in these ways, but like non-local in the other way, because the Fourier dynamics isn't local. And so it would be a locality concern which would make me reject it at that point.
So in that case, in the case in which are continuous internal labels, would you say that to treat them as internal is more or less?
You could treat them as internal, but it would.
So there would be no difference simply implied by the continuity of the labels.
Yeah. I hadn't thought about continuous labels, but it's if you had a continuous label, I would sort of intuitively combine it with the space-time dimensions, especially since it would commute with them in certain ways. There would be commutation relations and stuff.
Consider general relativity, the internal gauge group is the Lorentz group,
Yeah.
which is three non-compact directions.
Mhm.
So you, from the point of view of the Fourier analysis of this type,
Yeah.
they will correspond to three, how to say,
Mhm.
like R2. They have continuous labels, but
Right.
still we normally find it convenient to treat them as internal degrees of freedom.
Right.
With gauge theory.
Yeah. If you treated them as external, I think you would get into kinds of non-locality issues of the kind I just mentioned, in that the different Fourier variables are related to each other simultaneously, and so that's why I wouldn't choose to treat them as external space-time. But it's a locality consideration. So I've got like topology selection criteria working somewhere in the back of my head about which, there are many things I could spatiotemporalize, but certain ones seem preferable than others. And in that case I think it's clear, but in other cases it's not so much. Yes?
I mean, this is not a penalty, but here's a proposal on how you differentiate them, right? I mean, it is the case that if you do a Fourier transform, you require some nice regularity properties of your functions, right? And if you could engineer a physical scenario which would test against these regularity properties, maybe that would differentiate the theories even on an empirical basis.
I'm not sure. Insofar as the redescription is just via a Fourier transform, I would think there's a mathematical analogy at every stage, and it's, there would be an account for every possibility.
Maybe there would be something like a model of the quantified theory, which wouldn't be very good at accounting for the experiment, but wouldn't be easily molded into the Fourier transform description.
Yeah, maybe we'll have to think about that. I'd be happy to talk about it later.
The regularity condition you need to do the Fourier transform is the same regularity condition that you need to even put the scalar field as an action to define a mass term for the scalar field. So it's not any extra regularity condition here.
All right. Okay, I'll wrap up quickly. Maybe we can have some questions at the end too. The last 5 slides are just references, so don't worry about the slide. We're almost done. Okay. So what kind of reduction basis could be given if you demanded one of me, because I've kind of refused to give you one so far. Well, the way that I'm thinking about these things, and I built a bunch of mathematical tools, and they kind of push me in a certain direction. And I'm sorry I haven't showed it to you, but I'm pushed towards a kind of structural realism, which is more comfortable as epistemic, but I could go into an ontic place if you want me to. So to see why, let's recall how these space-time dualities work. And again, this example here is fairly generic in this aspect. One theory is about this type of particle or field on this space-time. And if we radically change the space-time, kind of radically have to change how the material stuff sits on that space-time, and we'll end up with that type of particle field on that space-time. These are radical redescriptions that come along with these topological changes. Okay, so if we do a BSA for space-time dualities, it very quickly becomes a best systems analysis for the types of entities which appear in space-time. Okay. So I can't say, oh, the world's full of this type of particle or that type of particle. If I'm really trying to find the common core, the sort of neutral ontology between all the space-time duals, given how differently they present each other, there's not really anything I can say about the types of entities which appear in space-time. But what is preserved under these kinds of redescriptions? Here's a bit of the mathematics of it, and we can maybe talk about this in terms of the Mobius-Euclid example. These, I'm making a distinction between kinematic possibilities and dynamical, so KPMs and DPMs. At the kinematic level, there are some structures, everything you need to state the dynamical equations. In the Mobius-Euclid thing, that was parallelness, distance, angle, other kinds of things. But you do equip your theories with some structures at the kinematic level, just enough so you can state the dynamics, right? It's the staging ground where you can even state dynamical equations, and then the dynamically allowed subset is picked out by that dynamical equation. That's roughly how I think of theories being structured. But what's preserved across these topological redescriptions is there's an isomorphism at the level of kinematics in a way that preserves the dynamics, despite representing that in very different ways. And this BSA is then invoked to determine the best way of representing this common structure. So what's being represented in alternate ways, what's being systematized, what's being, the thing which is being redescribed in possible different ways, is a kind of kinematic and dynamical structure of the theory, which is understood independent of what the states are actually like. And in this way, it's like space-time representation theory. Space-time representation theory is the title of a paper I have. It's like group representation theory is what I mean to say. And just a quick review of group representation theory. We've got some given group structure, something like SO3, and we can represent it as this kind of maps from, say, V5 to V5, where that's some 5-dimensional space, or from V7 to V7, where that's some 7-dimensional space. Okay? But we represent the group structure as different kinds of maps. Maps of this kind from this space, maps of that kind from that space. Now, if we think of these groups, just ignoring the internal structure of the elements of the group. G is just an element. Forget that it's this kind of map or that kind of map. There's a structural comparison which you can then do at that level, in which G5 and G7 are the same. They're isomorphic as groups. But if we start to look inside and find out how they're particularly representing the maps, then you find they're no longer isomorphic. They're not isomorphic as group representations. And I just want to say the same kind of thing about space-time dualities in general, and about this Mobius-Euclid example in particular. That they are different space-time representations of the same free-space-time theory, in a sense that I define more technically in the paper. But there's some structural core, which I've identified in the Mobius-Euclid case, and that's what's common between the two descriptions. One of them is just realizing that structure, or representing that structure, I should say, via maps from the real numbers to the Mobius strip, to like get a world line. And the other one is realizing it via maps from a different parameter space to the Euclidean plane, so picking out a world sheet in the Euclidean plane. But they're just different ways of representing the same structure as different kinds of maps from different kinds of spaces. Now, what makes this a point-like particle versus this line-shaped particle is just the structure of the maps it's represented as. What makes this being on a Mobius strip is just the fact that the domain of the space is the range of the space is the Mobius strip. Right? So you're both getting, with the specification of how the maps are realized, what kind of space-time you're on and what kind of object is in the space-time. And both of those come along together in the representation of the structure that they have jointly in common. And so if you want to take that as a metaphysical guide, you get to something like, what was I saying? Something like a structural realism. So what the world is a kind of structured unity. It's every world, or the world is like one model in this theory, and it has some structure to it at a kinematic level, a dynamical level. Maybe this is what Emily means by modal, but it's what I kind of mean by modal. And so you have the world and it has some modal structure, and then that admits different representations. It can be represented as this type of object on this field, and this type of object on that space-time. Right? And we have a best systems analysis which we can evaluate at that level, and I'm claiming that's the source of the significance, the source of the spatiotemporal significance of the space-time manifold. It only gains it by winning this kind of contest, or being the best way of doing this, via some selection criteria I haven't been able to fully spell out yet. Okay. So in conclusion, I wanted to minimize the spatiotemporal underpinnings of the Humean mosaic. We talked about Lewis, we talked about superhumanism, we talked about the regularity relationism. Each of those kept some aspect of space and time, got rid of many others, and then reintroduced those through a best systems analysis. But I want to go further and give this kind of best systems account for every aspect of space and time, including which relations are to count as spatiotemporal. And in the case study we looked at, we considered things like locality, type parsimony, low dimensionality. We considered all these things as aspects that might go into picking a space-time topology. And human phenomenology, I mean, we wanted to line up with what we kind of see. But what if aliens had a different phenomenology? Okay. So, and this is really just a pitch for my DPhil thesis. Our efforts to grapple with these issues would really be greatly enhanced if we had some new mathematical tools that really helped us get a handle over this kind of representation space for space-time theories. And that's what I built in my thesis. I call it the ISE method. I can tell you what the initials are for later if you like. It's a bit technical. But it allows us to do this. It allows us to move between these space-time representations, to remove and replace the topological underpinnings of our space-time theories, mathematically at least, just as easily as we can switch between different coordinate systems, or different law-like axiomatizations, or different geometric framings. I want to get our mathematical mastery of this kind of redescription to the same level we have with those others. And with all these options on the table, once we get them there, many of them might be horribly complicated. There might just be one good spatiotemporal description of the world, right? But we'd have to find that out. So we can investigate this space of all possibilities, and with some selection criteria that we need to do more philosophy about, maybe we can pin a kind of best systems analysis on this. Okay, and there are some references. So thank you for your attention.
Very little time for some questions, but there are yes and
I'm available at dinner.
Right.
Thank you, yeah. So I guess would it be correct to say that what you've given us is a best systems analysis like space-time, but that comes at the cost of not being able to have a best systems analysis of the dynamics, because you want the dynamics to be fundamental?
Yeah, in a way. Yeah, so the dynamical behavior of matter, well, it's what was in the Humean picture before the distribution of matter. So yeah, it's kind of my brute content, but it's
Because normally a Humean, I think, would want the dynamics to follow from a best systems analysis.
well, the laws follow from a best systems analysis. Dynamics is something else. Think of, when I say dynamics, think of causal powers. Maybe that's closer.
But a Humean would also want causal powers to come from a best systems analysis.
Yeah, I'm not a Humean in that way. So I'm okay with modally thick properties on the, like Heather Demarest has a kind of, best systems analysis that works for causal powers and such.
I mean, do you think this is a sort of general thing that we're not going to be able to be Humeans about both the structure of space-time and also the dynamics? We kind of have to pick one?
In a way, yeah, I think so. Because if you want to apply the BSA, like I said, to every aspect of space and time, I mean, the natural thing to think about is these space-time dualities as I have, and there's what's the common core in a generic space-time duality. Like, maybe case by case you can find some common core between these two descriptions. But if you really want to find the common core, not just between the two best descriptions, but between every possible way of describing things, the common core in that case will be just something structural. Right, and so I think you're pushed into a kind of structural view of the kind I think we both share.
Cool.
Yes. Any last question? Yes.
Just to round shot, but in what way, because you see your project as a renewal of Poincaré convention?
Yeah, a bit, yeah. So there was some work on conventionalism about topology, back in the day, but I've got a lot more examples, and now that we have, space-time dualities and such. So I've pitched this project as also as a kind of conventionalism about topology.
Okay.
Maybe not in the actual world. It might be that the actual world, looking around at the data we have, there's an objective choice, but just the possibility of conventionalism, that there might be creatures in some world who, and that the possibility of conventionalism justifies a kind of epistemic stance, I think, because if they're able to make sense of their world in which it's conventional and they nonetheless get around and don't bump into stuff, it just shows that there's a working, or it's possible that there's a working epistemology for it,
Then I suggest we thank Daniel again.
Yeah, thank you.